Hello everyone, welcome to another episode from Chedexcel. Today I am going to talk to you about the factors depend on forces of attraction. So in unit 2 we discuss about the forces of attraction or intermolecular attractive forces. So today we are going to talk to you about what are the factors that depends on those forces of attraction. So in unit 2 paper we are mainly tested with two types of factors. One thing is the water solubility, the other thing is boiling point. So we are going to look at how boiling point and the water solubility of a given compound or a molecule varies depending on their forces of attraction present. So we will see one by one how the both water solubility and the boiling point gets vary with the forces of attractions. Right. So the first factor is water solubility. Now the simplest idea is water contains intermolecular hydrogen bonding. So for a molecule to get dissolved in water, it should form intermolecular hydrogen bonding with water, or we say the water should have the ability to break the existing forces of attraction of that particular molecule, and it can form intermolecular hydrogen bonding with water. So then only they can get mixed or they tends to get dissolved. Now mainly what they ask from us in the paper, in Edexcel paper, is whether this one is water soluble or not, or sometimes they give it is partially soluble and explain the reason for that partial solubility. So the simplest idea is the organic molecules mainly they tested, they asked from us. So the molecules which contains an OH group, C double bond OH group, they tend to dissolve in water because they can form intermolecular hydrogen bonding. So if a molecule can form intermolecular hydrogen bonding, it tend to dissolve in water. Now there are molecules like this CH3CH3 propane. Propane does not tend to dissolve in water, or let us say hydrogen H2, right. They are very small or simple molecules, but they do not tend to dissolve in water. The main reason is CH3 and H2, these molecules are nonpolar, so they only have London forces. So they are not going to form any sort of favorable attraction with hydrogen bonding with water, any favorable attraction with water, so it does not tend to form favorable attraction with each other. Or we can say, let us say when hydrogen try to dissolve in water, if hydrogen cannot form hydrogen bonding with water, we can simply say it does not dissolve, or we say hydrogen does not have enough energy to break the existing hydrogen bonding in water, so that it does not dissolve in water. So organic molecules and simple covalent molecules, when they tend to dissolve in water, we mainly look at whether it can form hydrogen bonding with water. Now there are molecules that they do not have hydrogen bonding, but they tend to dissolve in water. For example, sulfur dioxide gas, hydrogen chloride gas, HCl. Now HCl also does not have hydrogen bonding, and it does not tend to but it does tend to dissolve in water. So when you look at what is the reason for that, so when HCl molecule is considered, it has polarity delta negative and delta positive. So the water molecule always have a polarity delta negative delta positive, right. So when you have HCl molecule, okay, I will write this one the opposite way, Cl here and H, HCl molecule, this is delta positive then. So they can form attractive forces, we call them as permanent dipole attractive forces with water, so they tend to dissolve in water. So if a molecule cannot form intermolecular hydrogen bonding with water, at least it should form permanent dipole attractive force with water. So if it does so, we can say it tend to dissolve in water. So simple covalent molecules such as ammonia, H2O2, they always have intermolecular hydrogen bonding. So if the molecule has intermolecular hydrogen bonding, it is very easy, it can form hydrogen bonding with water and it tend to dissolve. But some molecules they have intermolecular hydrogen, they do not have intermolecular hydrogen bonding, but they can have permanent dipole attractive forces. So they also tend to dissolve in water, not as great as the permanent hydrogen bonding, but they tend to dissolve in water. But the molecules like 100% nonpolar, they do not tend to dissolve in water because they do not form favorable attractions with water. So if they can't form favorable attractions with water, they do not tend to dissolve. So simply the molecules which only contains London forces are not water solubles. So alkanes, nitrogen, right, they do not tend to dissolve in water. But now oxygen is also nonpolar, but oxygen tend to dissolve in water because there are some different types of forces of attraction they can generate. We call them as dipole induced dipole attractive forces can happen, so they tend to dissolve in water. But I don't think they would ask those stuff. Normally they haven't asked. So everything what I tell here is the stuff they have asked so far from up to today, that means 2023 June. So up to now the stuff they have asked we can do with the basics. So if they have asked something else, we can just think about that, but normally they haven't asked those stuff. So the molecule tend to dissolve in water are simply the one which can form intermolecular hydrogen bonding with water. If not, it should be able to form permanent dipole attractive forces with water, and the molecules which contains only London forces are normally water insoluble, or they are not going to dissolve or mix with water. Now there are some other molecules like ethanol, CH3CH2OH. They tend to dissolve in water, but the molecule like butanol, they are partially dissolved in water. So that is a very common example of the question what they ask. Explain why ethanol is fully miscible with water, that means mixed with water, but explain why butanol is only partially soluble with water. Now the idea is this whole part of butanol, this whole part is nonpolar, which contains London forces. Here this part also nonpolar, right, CH3CH2OH, that CH3CH2 part is nonpolar, but it has a smaller carbon chain, so this is also nonpolar. So the OH group can form intermolecular hydrogen bondings with water. So delta positive, delta negative, 180-degree bond angle. Very commonly they ask us to draw this as well, right? Here also, okay, 180 should be there. Yeah, I'll draw this one opposite direction here. Okay, if I draw it here the same way. Delta negative, delta positive, 180 degree. Now the polar part, the OH group can form favorable attractions with water, so that it tend to dissolve, that part tend to mix with water. But nonpolar part, it doesn't have London hydrogen bonding and it only have London forces. The London forces are not going to form favorable attractions with water. But if the hydrogen bonding in water is strong enough to break the London forces, it tend to dissolve. So when you talk about ethanol, the London forces strength is less because it has less number of electrons. So hydrogen bonding in water tend to break the London forces of CH3CH2 group, so that it tend to mix with water completely. But in butanol, the larger nonpolar part is there, the longer the carbon chain, more and more London forces can form, so stronger the London forces. So when the carbon chain increases, the London forces strength is higher, so water doesn't have enough energy to break the London forces, so that it does not tend to mix with water. But the OH group can form hydrogen bonding with water, so the OH group tend to dissolve or mix with water, but not the nonpolar London part, nonpolar carbon chain. So the idea is this, the overall summary is this: when it asks you about the solubility of a polar molecule which contains both polar and nonpolar part, what we can say is, if the hydrogen bonding in water has enough energy to break the nonpolar part, it will completely mix with water. If not, it doesn't mix completely, we say it is partially soluble. So that is the other thing they have asked. but we don't know whether the London forces can completely be broken or not. We have to give it, they have to give it to us, explain why ethanol is completely miscible with water, whereas butane 1-ol, or we'll say hexane 1-ol is partially soluble in water. So when you are given it like that, we can explain it in that way. The London forces strength is stronger in longer carbon chain, so the water doesn't have enough energy to break the London forces, but it forms intermolecular hydrogen bonding with the polar OH group, therefore it is partially soluble in water, right. So like that you have to write. So we discussed 4 factors here. If the molecule is simple molecule which can form intermolecular hydrogen bonding, we say it is fully water soluble. If it is non-polar molecule, if it is a polar molecule but it's very simple one like HCl, still it can dissolve in water because it make permanent dipole attractive forces with water. If the molecule is 100% non-polar, usually it doesn't tend to dissolve in water. And the last factor is if the molecule has both polar and non-polar part, the polar part tend to mix with water, the non-polar part doesn't tend to mix with water unless water has enough energy to break the London forces. So those are the 4 parts we discussed. We have one last thing, the solubility of ionic compounds. So when we discuss about the ionic compounds, some of the ionic compounds are water soluble, some of them are not. Sodium chloride is water soluble, magnesium oxide is not water soluble. Both contains ionic bonding. Now the idea is both sodium chloride and magnesium oxide, they both contain ionic bonding, which means electrostatic attractive forces. So the simple idea is if intermolecular hydrogen bonding in water has enough energy to break the electrostatic attractions of that given ionic compound, it tends to dissolve in water. If the electrostatic attractions are stronger than the hydrogen bonding, then the ionic compound does not tend to dissolve in water. That's the basic idea. We learned this stuff in unit 4. There is a part called lattice energy and the solution enthalpy. So where there we are going to learn about even more details about that, but now just we can write if the electrostatic attractions of an ionic compound is stronger than the hydrogen bonding it can form with water, it is not going to dissolve in water. If the electrostatic attraction is weaker than the hydrogen bonding, then it tends to dissolve in water. So sodium chloride water soluble, Mg does not. So that is also they have to give us, explain why sodium chloride is water soluble but not magnesium oxide. Then we can write it like that. So the forces of attraction, when they mix with water, they form new forces of attraction type. We call it as ion dipole attractive forces. So ionic compounds contain ions, let's say sodium. So that sodium ion tend to form forces of attraction with water. We call it as ion dipole attractive forces. So water, oxygen is the one which make favorable attraction because it is delta negative. So normally they ask us to draw these stuff, have arcs. So you can draw it like this, drawing these 4 molecules. Sodium make favorable attraction with delta negative oxygen atom. Similarly, for chloride, it forms ion dipole attractive forces, but that is with the hydrogen, delta positive. So it forms intermolecular hydrogen bond, it forms ion dipole attractive forces. So why do we call it as ion dipole? Because sodium or chloride, they are ions, and this water molecule is polar, which contains dipole attractive forces as well. Even though we call it London forces, hydrogen bonding, they also have dipoles. So this is how we draw them when they ask us to draw how an ionic compound tend to dissolve in water. So for the cation, it is attracted to the oxygen of water. For the anion, it attracts to the hydrogen of water. So we call this one as ion dipole attractive forces, right. So this forces of attraction type, we call it as ion dipole attractive forces, right. So that is what we have to discuss. So those are the all major parts that you have to learn. So those are the 5 points. So if I quickly revise everything we learned right now, if the molecule is simple molecule and it can form hydrogen bonding with water, if it has hydrogen bonding with water like ammonia, H2O2, they tend to dissolve in water. Second one, if the molecule is simple molecule with permanent dipole attractive forces, it still tend to dissolve in water by forming permanent dipole attractive forces with water. The ammonia, H2O2, they form hydrogen bonding with water, permanent dipole attractive forces with HCl like molecules. If the molecule is 100% nonpolar, they normally does not tend to dissolve in water because they do not form favorable attractions with water. Fourth one we discussed is, if the molecule contains both polar part and the nonpolar part, depending on the strength of the London forces, it might completely mix with water or might not. That's where we discussed ethanol is fully miscible with water, but butane 1-ol is partially soluble with water, right? Because the London forces strength is stronger, then water doesn't have enough energy to break that one. So that's the thing we discussed there. The last point here, ionic compounds sometimes water soluble, sometimes not. If the ionic compound dissolve in water, the intermolecular hydrogen bonding in water is stronger than the electrostatic attraction forces. So here we can say the newly formed ion dipole attractive forces are stronger than the electrostatic attraction forces in the ionic compound, so it tend to dissolve in water. If the ion dipole attractive forces are not stronger enough than the electrostatic attraction forces in the ionic compound, then it does not tend to dissolve in water. So when they ask you to draw, you have to draw it like this. So those are the 5 factors we discussed. So that is how we can explain the water solubility of a compound depending on their forces of attraction, right? So in the next video I'll discuss how the boiling point of a molecule depends on the forces of attraction, and we'll come back to that in another video. If this is helpful, give a thumbs up and consider subscribing. Thanks for watching.